Okay, so today we will finish up the basically macroscopic stating our equations of change for multi-component systems, and then we will actually move on to solving problems. So let me open a new sketchbook. Here we go. So what is equation of continuity? Just for a general phase from our momentum transport. d rho dt is what? I heard divergence, then what?
Density by...
Okay, so this is something that we are very familiar with, and it's essentially mass conservation in my element, assuming that, you know, things are flowing in and flowing out, and I have to keep the balance of what's going in and out. Now, how does this change if I actually have I'm tracking down individual components? So now I'm actually interested in, we call that rho alpha, okay? What else do I need to add? So basically I'm individual component. So what is missing in this equation that I actually need to add? Source. So I might have some actual reactions going on and certain alphas changing to betas or whatever it is that I'm calling them. Okay, fine. So that's what I'm going to call plus R alpha. And then I turn this off. Come on. That's what I'm going to, oops, this device turned off. And then what else is missing? I'm now actually looking within the individual phase, and these alphas might be moving around because of the concentration gradients. Okay? So that's something that I need to add to this portion, and what is that going to be? So this is plus R alpha, and plus what? Or minus rather. Divergence of C. There's no C. I'm working with rows. Working with densities. J. Yes, what is J? What is J? The diffusion. What is diffusion based on Fick's law? Aye. Good morning. How's everybody doing? What type of flux is J? It's mass flux due to concentration gradients only and no convection. Okay? So convection I actually handled right there. Okay? So I need to add the part. So when we are typically looking at entire phase without looking at the individual components, we simply are not looking at J. We're ignoring it. Okay? So if I'm not ignoring it, and that's something that I'm tracking down for whatever purpose that I might be doing it, I might have something reactive moving in. If I inject something that basically spreads more by diffusion than anything else, I actually have to look at the contamination of my soil. Okay? Then I am actually interested in a specific component that I have in my water, not the water itself. Okay? Now, water moving around, of course, helps, okay, in the whole transport, but I actually have to look at that individual component and how reactive it is and what it is doing in my subsurface. So basically, that is now the difference. So we're looking at all of those individual components. So this is something that we stated, and basically, how will I get back to my equation of continuity? So this is equation of continuity for individual component, okay? And I go back to my equation of continuity by essentially summing up all of these equations for all individual alphas, and then the fact that all rho alphas sum up to rho helps me out, and also the fact that all J alphas sum up to 0, okay? Because I'm actually looking things relative to each other. that helps me out. And when I sum up all R alphas, I get 0 as well because of the conservation of mass. Okay, so basically this is what we derived last time around, and this portion here, so I didn't write it next to each other, but this and this, I also have a different name for it. It's divergence of combined flux. So that is basically my flux that has both the portion that is moving due to the concentration gradient only as per Fick's law and convection. So that's why it's combined. So it's diffusion and convection combined. Yes?
If we have multiple phases, then we would have this set of three terms for every phase.
Yeah. And then you would have to be careful, are those phases immiscible or not? If they're immiscible, then everything is just true, or this equation is true within that phase only, and I'm not losing anything on the boundary. But if they're miscible, then I have certain flux through the boundary, so that enters as a boundary condition for that phase. Okay. So there's an exchange term that might play a role.
An extra source.
Yes. So if you have this course is basically focusing on single phase transport for the most part only. The way you have Navier-Stokes equation, for instance, for multiple phases, then Navier-Stokes is true within each phase, and each phase has its own viscosity, right, and density. But then at the boundary, I have an additional forcing term that is due to the capillary forces and shows up only at the boundary. That's for immiscible fluids. Okay, so you will simply have an extra term that is basically added only for points close to the boundary, that is this forcing due to the capillary forces at the boundary. Other than that, you will across that boundary also have a jump in viscosity, jump in density, so jump in the properties, but other than that, the equation is still valid. Okay. Now, if you're upscaling things to Darcy's law, then you will also have Darcy's law, but you will have the relative permeability, not just permeability. So it's the permeability, there's a coefficient that will multiply absolute permeability that is basically telling how are things moving within the phase that you're looking into. Okay? And you're looking at the gradient of pressure within that phase. Okay? So things are technically, all of these fundamentals that we're doing for the single phase flow are valid for two-phase flow. They're just, of course, more complex if you have multiple fluids. And welcome to petroleum engineering, you always have multiple fluids. You're rarely in a single fluid situation, because one of them you're trying to get out by chasing it with the others, right? So essentially. And then one thing that we're actually not really incorporating in this, but plays, of course, the big role, it's thermodynamics and phase changes. Okay? So all of these equations are valid knowing where your phase is and hoping that your phase didn't turn into something else. So whatever was oil might have volatile components, and it might actually change into gas. So you suddenly actually, and that's often a problem, at certain depth and pressures, you will go from a single phase situation to multi-phase situation. And then the moment you have multiple phases, they're going to start blocking each other, and that's a problem. Okay? So essentially, you actually need to couple the thermodynamics as well. But typically, you again, just like we do in decoupling any problems, you kind of work with the phases, then you know at certain pressure and temperature that you need to change, and then you, from that point on, you solve different type of equations. But you kind of have to know it's happening. And of course, it's a complex situation to just work itself out. Anyway, where was I? All right. So now we have this similar situation, or the similar equation I will also have for if I'm actually looking at the molar quantities. So basically, my molar quantities will give me something like this. Partial C alpha, okay, is equal to equivalent version of this, so essentially, wait a second, okay, of N alpha, so this is my uppercase N now, N plus R alpha It's just that when I sum this one up, okay, all of my reactions R alphas for molar quantities don't necessarily sum up to 0, so that's going to hang in there in the equation. So if I sum this up, I'm going to get something like partial C partial T is minus CV star and plus the sum of all R alphas, again, because I don't have necessarily conservation of molar quantities. Okay. Now, there is one more, so now I'm just going to write down a couple of special cases that are typically used in solving problems. So this term here, the divergence part, so often I'm actually going to things, I'm not going to, density of entire phase is something that I know, and it typically comes as a known constant into my system, okay? And I'm typically keeping it constant for most of the problems that we're solving. So it's typical to write equation in terms of omega alpha, and omega is that fraction, right? Rho alpha over rho. So when I do that and also rearrange a little, this equation here becomes this partial omega alpha partial t. So basically rho I'm treating as a constant, so I wrote that rho alpha is omega alpha times rho, right? Plus, and also it's typical to do this, and that takes a little bit of rearranging and applying the equation of continuity a couple of times. I'm not going to do that, but just trust me that it works out to be this. And one more thing, especially if you have a binary system. What is this? Do you remember? I'm not hearing well. My hearing is bad on Wednesdays. Material derivative, that's correct. So this is actually d omega alpha dt. So the short way to write this is dt is minus plus r alpha. And then the special case that we actually use the most times, or two special cases that we use the most times when solving problems, is the following. I'm going to assume a binary mixture, which often means there's like a species I'm tracking and the others are just lumped into one. So I'm just going to, in case of a binary mixture, and also a dilute system at constant pressure and temperature. In that case, my rho DAB is approximately constant. So my Fick's law actually says so that my divergence of J alpha is actually minus divergence of rho DAB gradient of, I'm just going to translate everything to now A and B because I have a binary mixture. And since this is a constant, it can actually come outside, which is helpful because then I have the equation written in terms of omega A. Okay? So my special case will then be rho d omega A dt is equal to rho DAB Laplacian of omega A, because divergence of a gradient is Laplacian, plus RA. I keep mixing alphas and A's. And how do I get omega B? Well, omega B is simply 1 minus omega A. So again, this is special case for these binary mixtures and dilute cases where my rho DAB is approximately constant. And if you remember what we developed rho DAB, and it was a function of temperature and pressure, so if those are constant, then we can definitely assume that it's constant. One more simplifying case, so simplify further. In case that I actually have a static system for stationary system, my V is 0, okay? So that's, for instance, diffusion in solids. And I have, with no chemical reactions, then this material derivative is simply a derivative in time because my V is 0, right? So I have V dot, this V is 0, so that's going to be a simple derivative. So, and RA is 0 here, so what I'm going to simply have is that rho partial derivative of A partial T is rho DAB Laplacian of omega A. So rho, of course, I can divide by rho. Do we recognize this equation? Which type of equation is this? It's a heat equation. So heat equation is omnipresent. It's also Fick's second law. And we will bump into this equation all over again. I will reserve the class on Monday to basically solve it. So we will go back to chapter 4.1 that we skipped at the end. But I will show all of the cases in our entire course where this equation shows up. And for simple 1D case where this is just second order derivative with respect to x, we're going to solve it. Okay? But it's basically applicable across all types of transport where this shows up as a problem. It's just that your coefficients change. Transport coefficients change, yes?
On the first case where you say dilute, that means that the density is equal to what?
Dilute is basically the fraction of A is very small. So I don't have a lot of A inside this space.
The fraction of A is very small.
Yeah. So that's what I mean by dilute. Concentration is low.
Okay, so P is going, okay.
So low as in low concentrations. Because at those cases, the higher you go in concentrations, your DAB starts getting dependent on rho A. Or how much of that.
Okay.
Right? So that becomes a problem.
Okay.
Okay. So this is also heat equation. And of course, if you have a stationary case, so you don't have time component, that's my Laplacian of something is equal to 0 is Laplace equation. Again, it's a famous equation. All right, so we will just now state the equivalent for these in case of molar quantities. So for molar quantities, and that's a little more used for gases, so this is a special case, again, but molar quantities. Again, if you have a dilute binary system, you will equivalently assume that CAB is approximately constant in dilute binary system. And these two equations become then C partial, so I don't have omega, I have now X A T plus, it's not V, but now it's V star. I'm not calling this material derivative because material derivative is not defined with V star. Okay? So it's C dAB Laplace of XA. And now the part that is a little, those were some of our A's, but this actually comes down to, when you work it out, to XB RA minus XA RB if you have reactions. And the similar is true for XB, or you simply say XB is 1 minus XA when you solve for that. So XB and of course, if you had a stationary system, so V star is equal to 0, so stationary would give you also heat equation for Ca, so partial Ca partial T is equal to Xa, actually. Well, it can be turned into Ca partial C dAB Laplacian of Ca. So again, that's again Fick's second law. Okay, you're done with formulas. Let's apply them. Our first example is diffusion. Through a stagnant gas film. This is also chapter 18.2 in BSL. So we have a situation where I have liquid A and this is liquid, and I have gas B on top of it. And this is what I'm going to call here Z is equal to Z1. And here at the top, so what I have is basically vapor of A is going up and diffusing through B. Okay? So vapor of liquid of A diffuses through stagnant gas B. And here at the bottom, I'm actually constantly, if my interface, because of all of the vapor coming off, is going to change, I assume that I have supply of A constantly coming in and keeping this at the same location Z1. Okay? So this location of the interface, so interface location is kept constant. Well, essentially I have some source of A is necessary, okay? And
my XA is XA1. I just know what it is. It's essentially concentration of A corresponding to equilibrium between vapor and the liquid. So basically my XA1 thermodynamically is partial pressure of vapor divided by overall pressure. And also I have boundary conditions such that I can maintain a constant level of XA at this top boundary. So maybe I have some fan that is taking off any excess of A, so I'm always keeping it at a constant that I can control. So those are my boundary conditions. All right, so let's solve for concentration of A. This is presumably a cylinder, but my boundary conditions are kept constant on top and bottom. Okay? There's nothing in the problem that would actually give me variability across a single surface or cross section in z direction. So I can actually just assume that this is a one-dimensional problem. Okay? Because if I had any variability with respect to radius or something like that, well, I would have to have boundary conditions that have such variability. Okay? So this is something that is essentially, we can just look at the z. So z direction, the only relevant one. And yes, you could go and set it up in two-dimensional problem in terms of both r and z, but that's essentially overdoing it. So this is we're going to work this problem in two ways, one with shell balance and one with just ready-to-go formulas, so you can see the difference. So basically, if I have a shell, well, shell looks something like this. So this is my z and z plus delta z. Okay. And there is stuff coming in here and going out here. Without solving this, can you tell me what this equation is going to look like? ddz of something is equal to 0, right? No reactions, so therefore 0, steady state. Now, what is that something? N, yes, N, uppercase N, my combined flux. Okay, well, let's get there. So basically the way we do shell balance, so if you remember in heat equation, the first problem we solved was dEz dZ was equal to 0, right? So you can, in a 1D problem like this, you can actually expect that equation. And if you have reactions or something else as sources, then it's not going to be 0, it's going to be that some source, whatever that is, right? So basically, rate of mass of A coming in minus rate of A coming out. No reactions, so any production or reaction or sink. So that's going to go away because we have none, is equal to 0. So if I assume my cross-sectional area I normally refer to as A, but here I'm going to call it S, then that area S times basically my NA, okay? But NA, only the component orthogonal to the surface coming into my shell. Which component is that? at Z, so that's stuff coming in, minus surface area times NAZ at Z plus delta Z is equal to 0. I can, of course, divide by S delta Z, which is the volume of my shell. And when I do that, I'm going to get minus NAZ evaluated Z plus delta Z is equal to 0. And this, of course, becomes a differential equation. Everybody done? Okay. So I will get, when I shrink my shell, D and Z and AZ dz is equal to 0. So I can just remove that minus. And that is the basic equation I'm solving. Of course, it looks very, very simple when it's stated in terms of combined flux. And that was the case throughout this course. Now we actually have to look into NA. Well, let's recall what NA was, and I'm just going to write in terms of general vector terms. Of course, we're going to look at the Z component. This is my JA plus CA V star. So by definition, this is my flux, basically just diffusion only, and any convective component coming in. So basically, this is when I look at my NAZ. My basic problem here is that I'm never solving in terms of NA, so I have to come down. My boundary conditions are in terms of XA, so I have to basically boil down my equation to something using XA, because that's what I'm solving for, right? And that was also my choice of molar quantities, because that's how my boundary conditions were given, okay? So don't overthink it. If boundary conditions say so, that's the molar versus mass quantities that you choose in mass transport problems. All right, so this is JAZ, which is JA, I can actually express it as minus DC DAB, partial XA, partial Z. So this is my Z component of my flux as per Fick's law, okay? And plus my CA, what is VZ star by definition, or V star by definition? It's my average of all components using these fractions XA and XB, so it's gonna be actually XA VAZ plus XB VBZ. And this is where, in this problem, we're actually lucky. Normally, you kind of have to actually know what VBZ is, okay? And that can be a problem, or you have to express it somehow. Here, I'm dealing with stagnant gas, so I'm actually just going to assume that it's 0, and it's a dilute problem. Okay? So I'm just going to assume it is 0. Otherwise, you kind of have to figure out what it is. So both VBZ, and that's essentially my NBZ, if you will, are 0. That's lucky. Otherwise, I have to figure out what is NBZ in terms of NAZ Otherwise, I don't have things expressed only in terms of XA that I'm solving for, right? So that's what's gonna throw in variations to these problems. There will be various reactions and so forth. If I have a reaction coming to the surface and off the surface something else is coming off. So I have A approaching the surface and then I have a reaction happening and B is coming off the surface. Then based on the reaction that is happening, I actually have to figure out what is the flux of B coming off the surface in terms of the flux of A coming to the surface. Okay? So that's where actually boundary conditions will actually come into play with this reaction to tell you what NBZ is. Okay? So those are the variants of these problems come with different sort of applications and different cases, and that's basically what changes the equations here. But for now, we're lucky this is the simple initial problem. So basically what I have here is, this is equal to, minus C dAB. I can just switch to regular derivatives because I have only derivative with respect to A dZ, with respect to Z, I'm sorry, plus. This is actually, I'm gonna write this as XA, this is XAC times XA VAZ. Or I can just, why did I do that? I can just rearrange it. So I'm gonna write it as XACA. Because this is NAZ by definition. So basically I have NAZ is equal to minus C dAB dXA dZ plus XA NAZ. So essentially I have 1 minus XA NAZ is equal to minus C dAB dXA dZ. In other words, I'm finally expressing NAZ in terms of XA, and that is minus C dAB over 1 minus XA dXA dZ. And that is essentially what I need to plug it back into the dNAZ dZ is equal to 0 and then solve for XA because I have boundary conditions in terms of XA. So essentially, my equation is ddz of C dAB minus XA, space, is equal to 0.
C is a constant, right?
Yes, C dAB is treated as a constant. So I can divide, so this is constant for dilute binary system. At low pressure and temperature. So I can just divide by it. So what I'm really solving for is 1 over 1 minus XA dXA dZ is equal to some constant C1. And the way to integrate this is simply to separate dXA and dZ, integrate so basically I have minus ln of 1 minus XA as C1Z plus some C2. Everybody agrees with me? So this is ready for boundary conditions. Minus ln of 1 minus xa1 is c1 z1 plus c2, and minus ln of 1 minus xa2 is c1 z2 plus c2. And you would subtract the two to eliminate C2, express what C1 is. I'm just going to state the solution. So dot, 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 C1 is minus 1 over Z2 minus Z1, ln 1 minus XA2, 1 minus XA1. C2 is another complex variation of this. So if you remember, my initial was minus ln of 1 minus xa is equal to c1, which is this big thing, times z plus c2, which is this other big thing. And c2 also has a similar term like ln 1 minus xa1. So this could be actually rearranged. After a bit of rearrangement, you would get that ln of 1 minus xa, divided by xa1 is z minus z1 ln 1 minus xa2. And this can actually, so this term can actually go as an exponent, and then you can do E2 of this entire thing, and that will give you that 1 minus XA. 1 is 1 minus XA2. 2, Z minus Z1. Now this kind of looks scary, but this is really sort of like a normalized XA or version, normalized XB actually. What did I do right here? This is actually XB over XB1, right? This is XB2 over XB1, right? So this is just a number that you have based on the boundary conditions. And this is sort of a normalized length. So it's not as scary as it looks. And this is really XB over XB1. So this is like normalized XB. Because XA plus XB is 1, correct? And this is really XB2, B1, and it's constant, right? So it's some constant to the normalized Z. So it's not all that bad. All right. Now, what would happen if I actually had ready-to-go equations? Okay. What if we used equations of change instead of shell balance? Then you would have that equation of change that is applicable here is C times dxa, this is one of those special cases I wrote down, plus V star dot, xa is CDAB XA plus XBRA minus XARB. And luckily, there are no reactions here, so this is a 0. So this is almost in the form I needed. So I have boundary conditions in terms of XA, right? And I want to solve in terms of XA. The only thing that is bothering me here that I have to sort of express is this part here, right? So this is not in terms of XA yet. And this is actually, so I have steady state, so this is going to be 0. So basically I have to relate this to XA in order to actually have an equation in XA. So in the previous shell balance, we have to basically express NAZ in terms of XA, and here I have to do it with V star. So either way, no really free lunch. So basically, if I look at the Z component of this, because that's the only thing that is alive here, it's CVZ star. And gradient component in Z direction is DXA DZ. Again, I have only dependence on Z, so I can is equal to C DAB. And this Laplacian simply becomes D square XA DZ square. So this is my Z component of the vector equation above. Now let's see what CVZ star is by definition. It's C times XA VAZ plus XB VBZ. This is, again, luckily, the B part is 0 in this case, just like we had before. So that's actually CXA, that's CAVAZ, and that is by definition NAZ. And I would again have to express NAZ in terms of XA. This work I already did before. Okay, so so we had it before. It's minus CDAB over 1 minus XA DXA DZ. So my point is, either way you go, shell balance or equation of change, you will have to express either V star or NAZ in terms of XA, okay, in order to actually get the equation in XA that you need to solve. And that's the key part of solving mass transport problems that wasn't there before. So once I do that, so I have to plug this into here. I will have CDAB on both sides that I can get rid of. So then that becomes, I'm just going to write it on the same page. So I don't open another. Basically, I have minus 1 over 1 minus XA DXA DZ is square. When I divide by, and this is the standard problem with equations of change. We got like a second order equation ready to go. Whereas when you do shell balance, you kind of do step by step and it's clear what to integrate step by step. Here you actually have to now go and do some guessing how to transform this and actually get the similar solution as before. So that is the key. You would have to kind of play, well, what if I had DDZ of this, what would I get? And then try to express the second order derivative in terms of it. So you have to get inventive, okay? So this is the key issue with having, if we actually had a constant here, wouldn't be a problem because those linear equations we know how to solve, but we actually have a function of XA, okay? So again, I'll leave it to you which one you're more comfortable with in solving. I believe that shell balances are a little easier to actually integrate as you're solving the problem. Okay, so this is just to show you the difference. All right, Thank you, and I see you on Friday.